Welcome to the Energy Capital Podcast. I'm your host, Doug Lewin. For this episode, I had the pleasure of talking with Michael Weber, a longtime mentor and friend and a professor at the University of Texas at Austin and celebrated author. I took his short course on energy technology and policy over 15 years ago, and it was foundational and even transformational for me. Michael has always been a great public intellectual throughout his career. He's an engineer and he's a policy expert. He can get into the weeds of policy and technology as much as anybody, but he also does a fantastic job translating very technical and complicated concepts and issues to make them easily understandable. Michael has made energy literacy a north star of his career, working to help people understand that whenever someone presents any energy issue as black or white, you should be suspicious. There are trade-offs, and it's important the public understand them. Michael has always worked to make complex energy issues accessible to the general public, including a 6-part series on PBS based on his great book, Power Trip, The Story of Energy. I recommend both the book and the PBS series. He also wrote Thirst for Power, exploring the many connections between energy production and use and water use, which was turned into a 1-hour documentary. Again, highly recommend. He created a show and eventually a class called Energy at the Movies, exploring all the ways energy makes its way into Hollywood. And his latest book comes out on February 14th, 2024, called Powering Humanity: Essays on Energy and Society. It's a great compilation of over 50 essays Michael published over the last 14 years. It's a great read, both for what he got right and what he got wrong. Again, I highly recommend it. Michael is the Josie Centennial Professor in Energy Resources at the University of Texas at Austin, and he's also the Chief Technology Officer of Energy Impact Partners, a $2 billion cleantech venture fund. I could have easily asked Michael hundreds of more questions. He's a wealth of knowledge and a fantastic explainer of hard-to-understand concepts. Please enjoy this episode, and please share it with others who might have an interest in energy as well. And last but not least, please leave us a 5-star review on Apple Podcasts or wherever you listen to podcasts. Thanks for listening to the Energy Capital Podcast. Michael Weber, welcome to the Energy Capital Podcast.
Thank you so much for having me. It's good to be in a conversation with you in this format after all our conversations in person over the years.
Yeah, I mean, one of the reasons I so wanted to do this podcast was just to have conversations like this. I always enjoy talking to you, but I'm not sure we've ever just had an hour to talk. So this is great. I've been really looking forward to this. And just before we jump in, just want to acknowledge the influence you've had on me and so many people around the state and around the country. I think it was was it Energy Policy and Technology short course back in
energy,
like 2000s? Yeah.
Yeah, Energy Technology and Policy, which you took like in 2008 or something. It was a while ago.
That's right.
So,
that's right. Yeah. And that was one of the first times that I really felt like I could really understand this stuff. Your ability to kind of translate really difficult concepts into plain language and help dumb people like me understand it is so appreciated. So thanks, and thanks for being on the podcast.
Oh, my pleasure. And thanks for the kind words. It's exciting to be a collaborator with you after all these years.
Let's start just, if you would, just kind of describe in your own words who you are and what you do.
So it's great. So I'm a professor of mechanical engineering at the University of Texas at Austin. So I do research and teaching on energy and the environment, really at the convergence of commercialization, technology, and policy. I'm really an engineer, but I say the words describe me are engineer, entrepreneurship, and energy, the 3 E's, so to speak, and maybe add the 4th E of environment. I'm also Chief Technology Officer at Energy Impact Partners, which is a $4 billion cleantech venture fund. And I was formerly Chief Science and Technology Officer at ENGIE in Paris, France. So I was there for about 3 years, 2018 and 2021. So I was an executive in charge of research innovation for one of the world's largest multinational electric and gas utilities. So I've got a lot of corporate experience, some venture and entrepreneurship experience, and a lot of academic perspective.
Yeah, and also just this kind of quintessential like public intellectual, right? The talk also about just for a minute about the PBS series, because I want people to be able to find that if they want to learn more after this conversation.
Yeah, so I'm a public intellectual, which means I mouth off in public. I write op-eds and give speeches and publish essays. I've written several books, and one of the books, Power Trip, The Story of Energy, has been turned into a 12-part PBS series over 2 seasons. Season 1 came out in 2020, and season 2 just came out a few months ago. It has 12 hour-long episodes on energy you can get on at PBS and Amazon Prime and Apple TV. And if you fly American Airlines, it's in their in-flight entertainment. Season 1 is. You can watch it while you're captive on the tarmac or something like that. And then I've got a new book coming out on Valentine's Day called Powering Humanity, Essays on Energy and Society, which is a collection of like 65 of my 200 plus op-eds and essays I've written over the last 15 years. And that one's a fun one because I go back and actually assess when I was wrong or when I was right, because I made a lot of predictions about the future in those essays. So that's my upcoming book.
Yes, and you were gracious enough to provide me an advanced copy, and I love it. I've been looking through it over the last couple of weeks, and it's great. Highly recommend it to everybody, as well as Power Trip, Thirst for Power. Anything Michael's ever written or recorded is worthwhile. All right, let's start with, usually, Michael, I save a few questions for the end to kind of wrap up conversations, but I actually want to invert the order today and start with these because you are an expert in such a wide range of different topics related to energy. I'm really curious to hear what your answers are to these, and I think that'll help guide our discussion. So I want to start with this question that I ask on most of the podcasts. What is something that's conventional wisdom among energy people that you think is wrong or commonly misunderstood?
I've got so many. There are like three things that come to mind that are conventional wisdom that I think might end up being wrong. One is that to decarbonize the economy, we have to get rid of oil and gas or oil and gas companies. And I can see a lot of ways we could decarbonize the economy with molecules still in the mix and with those companies still in the mix. Another piece of conventional wisdom is that we will have to have baseload power in the future. And I think the whole concept of baseload actually is going to go away. And we're going to replace it with dispatchable, but that means dispatchable on and dispatchable off. So we could talk about demand response for things you could turn off, as well as power plants or batteries or things you could turn on. So the concept of baseload, I think, is just going to feel very antiquated. And then a third piece of conventional wisdom is that hydrogen or other clean options will always require subsidies to be cost competitive. I don't think that's true. I don't even think it's true today for wind and solar. And I don't think it's going to be true for hydrogen in the near future. I think instead, what we'll do is instead of subsidizing one form of energy another, we'll quit letting emissions pollute for free. I think like you think of like a dumping waste in the atmosphere for free is a form of subsidy. I think if we eliminate that subsidy, then we'll move towards the right answer and won't need to subsidize the clean stuff. So there's this notion like, oh, we got to have hydrogen tax credits, that kind of thing, make hydrogen competitive. Not really. We maybe just can't let people pollute for free anymore.
We're going to come back to all three of those as we go through. Those are great ones. As I suspected, your answer would be interesting there. Another question I like to ask: what will the grid look like in 10 years, and how will it be different for consumers? Just for people that don't think about energy every day, but obviously, depend on the grid, rely on the grid, and pay for it. What's it going to look like in 10 years? How will it be different for them?
I've got a couple thoughts, and I've got to be careful to be honest, and I'm mixing partly what I wish for and what I actually think will happen. So what I think will happen is coal will continue its decline. Coal's already dropped like 60% in the last 15 years. I think it drops another 50% from where it was in the next 10 years. So coal about a decade from now will be about 10% of where it was in 2006. And that's really phenomenal that coal will end up dropping about 90% in 2.5 to 3 decades. A lot of that's because of the natural asset life of the coal plants. The coal plants are coming up at their end of life retirement window, and we just won't replace them. There are a few newer coal plants that might hang in there, but most of the coal we use in America will be for like steel and cement, not for power. There'll be very limited coal in power, and I'm pretty confident that will happen. A thing that I kind of wish will happen, but I don't know if it will happen, is that we pass through a lot of the market reforms we've done on the wholesale side to the retail side. So if you look at places like Texas, there's a lot of competition on the wholesale side. A lot of new power plants can come in like wind and solar or clean gas or whatever it is. But most of us on the retail side still pay bills the same way we did 10 or 20 years ago. Our bills look kind of the same. And I think we need to have a lot of evolution there where we can be paid to turn off our power certain times a day. We can be paid to sell power back to the grid. If we have solar, we'll have much more net metering, might even have peer-to-peer markets where we can sell power to our neighbor. There's a lot of things that could happen on the distribution end of the power sector that haven't happened yet. That would be great if they happen, but that's my wishful thinking. Like that's what I wish will happen in a decade. I don't know if that will really happen or not. And then the thing that I do think will happen and I wish will happen is I think we'll have a lot more distributed generation. a lot more rooftop solar panels. However, as a warning to everybody, that distributed generation will also include natural gas generators, maybe fuel cells and things like that. It won't be just rooftop solar. But I think we're going to have a lot more distributed generation, or a lot more generation at the end of the line because of all the difficulties we're having building transmission and for other reasons. So that's kind of a mix of things I think will happen and things I kind of hope will happen. In that middle one, this evolution of having more sophisticated and efficient markets at the distribution end would really enable that third piece of distributed generation.
Yeah, that's right. I think it's interesting. You mentioned both solar and gas. And of course, I think storage will probably be part of that mix too. Battery storage would be part of that mix too,
Absolutely. And
whether it
that
be in
battery's
EVs or on the wall. Yeah.
exactly. And we actually, when we remodeled our house a decade ago, we built in a place in a crawl space for battery storage, like a power wall or something. And we'll probably never use it because the battery in my electric vehicle is so much larger than whatever power wall I could have bought.
Yeah. Yeah. A lot happening in that space. All right, good. We'll come back to all of those things as we begin to talk too. And then the third question I like to ask when we have time, and I knew if we started talking about other things, we'd never have time. And I wanted to ask you these questions because you do teach a class on policies and technology. So, what are the two or three, one, two, or three, whatever you like, energy policies that you think could have the biggest impact to increase reliability, lower costs for consumers, and reduce pollution?
That is a great question. So I kind of gave a hint at this with the first question and part of my answer, which is I think we need to put a price on pollution. Like if I think of the policy we need that's missing today is we allow people to pollute for free. They can dump their greenhouse gas emissions in the atmosphere for free and use our atmosphere as a common dumping ground. That is inappropriate for so many reasons. It's inappropriate economically and ethically and morally and environmentally, you name it. And that's the one policy I really wish we had. And if you ask like 99 out of 100 economists, they would say, put a price on carbon. That's the most important thing you do. And that carbon emission is a proxy for some of the other problems we have around domestic security of our energy sources, reliability of the grid, and everything else, because that CO2 ends up driving climate change, which becomes a forcing function of strain on the grid. So if we put a price on pollution, it will lead us to cleaner domestic mix of sources that will end up being more reliable. And then the counterpoint to that is we should have a reliable services price, like a market for reliability services. And we have some of that, like in ERCOT, we'll have spinning reserves and non-spinning reserves and reg up and reg down, these different types of markets that pay people for the reliability services they provide. And I would like to see a more enhanced, bigger market for that. Most of the market is just for buying and selling electrons or electricity in the power markets. And a little bit of the market is to do so reliably. And I think the reliability part of the market should grow and will grow. And that will incentivize not only more capacity, the more things we build, but more things like storage and demand response and dispatchable firm clean power and this kind of thing. And so I think having a price on pollution, so you can't pollute for free anymore, and a value or reward for reliability, those two things hand in hand will do a lot to solve our grid. And we don't really put a price on pollution at all. There's sort of a price on some of the pollutants like NOx and SOx, but not CO2. And we have a little bit of a price or a little bit of value that we attribute for reliability, but I think we need to do more of both.
Yep. Uh, all right. So this is great. I think my instincts were good on this. Asking these questions sort of tease up because as I was preparing for this, there's like so many things I want to ask you, but kind of getting a sense of where you want to head is helpful. So I actually want to go back to the first thing you said about what is commonly wrong, taken as conventional wisdom, that the decarbonization requires an end of oil and gas. Um, I want to talk more about that. So obviously, you and I both live in Texas. This podcast is focused on Texas. Texas has, back to Spindletop, taken a very large share of its wealth. It's not as much now as it was, 80 years ago or whatever, but it's still a very large share of the wealth generated in the state. The tax revenue in the state is tied to oil and gas. So I think a lot of people that either have derived wealth from that, continue to, or tax revenue or whatever, get very worried when they hear energy transition. Why should they not be worried? Why do you think that it could continue? Is this even potentially an opportunity as well as a risk?
It's absolutely an opportunity for oil and gas companies if they choose to be part of the future. And not all oil and gas companies wish to be part of the future, to be very clear about that. Some of them are at war with the future, and I think the future is going to win, frankly. But there are a lot of companies that feel like they have a role to play. There are a lot of solutions in the decarbonized economy that require subsurface expertise. It might include like geothermal energy or below ground storage of hydrogen or even extraction of hydrogen from natural reservoirs. It might include CO2 sequestration. It might include pipelines that move different molecules around, including CO2. It might include offshore solutions like wind or solar. It might include a lot of the things that the oil and gas industry already knows how to do better than anybody. And so there's certainly a skill set that oil and gas has, a capability that I think we're going to need in the decarbonized future. And that includes things as basic as project finance and project management. And how do you do complex engineering projects in hostile environments and make them work? That's something oil and gas knows how to do. So there's a skill set that's very valuable in the people they have on the team, the geologists, the engineers, you name it. In addition, the product they sell, the molecules might also be important. Now, the molecules might be different in the future, and they might be sourced differently. The methane might not come from below ground fossil reserves, or if it does, it might be converted into hydrogen, or it might be methane that's manufactured from biological processes like decomposition of animal manure or something like that, or it might be other molecules like ammonia, formic acid, or hydrogen, methanol, you name it. But the world of moving molecules around and converting molecules is something oil and gas knows very well. So these molecules might play a role. And then as you especially think about the molecule of CO2 and removing it from the atmosphere and putting it somewhere else, that's something oil and gas companies might know how to do. So that I just feel like there's a bucket of incredible capability and expertise and assets like rights of way and pipelines and platforms and ships and welders. There's welding equipment. There's a lot of assets as well as skill sets that I think will be really useful. So that's kind of my view. But you don't have to take my word for it. You can listen to ExxonMobil CEO Darren Woods, who said on the record in the middle of 2022 in an interview that his view, and therefore ExxonMobil's view, because this was on the record, is that 100% of light-duty vehicles sold in the world in 2040 will be electric. So this is a man who sells gasoline for a living saying the new cars that you buy by 2040 will be electric and will not need gasoline. And he said, that's okay. Those cars are going to need a lot of lightweight materials like plastics and other advanced materials. Well, we make those materials, we'll be fine. And so if one of the world's biggest sellers of gasoline says the market for gasoline will disappear, but that's okay because we'll make the materials those cars need, for example. He didn't say this, but they'll also produce the natural gas that will make the electricity for those cars. They're fine. And so that's one view. Another view tends to be like smaller independent oil and gas companies who don't care and are going to ride the fossil tail. Like they're just going to ride the curve down and make a lot of money before they retire and that kind of thing. So they're not going to switch to the future. But some of the big ones, the multinational companies for sure, are switching to the future. So that's my view and that's their view, frankly. But the way I put this in sort of a logical hierarchy of decarbonizing is it's kind of a 4-step process. Step 1 is efficiency. We should make things as efficient as possible. Light bulbs, cars, homes, you name it. We need to reduce the height of the hurdle we have to clear, or reduce the height of the mountain we have to climb, whatever your analogy is. We have to use less. That is the best thing we need to do. By the way, that's a very hard thing to invest in as a venture capitalist. And so efficiency doesn't always get there with market forces alone. It's a great place for policy, especially around building codes and fuel economy standards and that kind of thing. But efficiency is where we start. The second thing is electrification. We need to electrify as much as is reasonably possible, especially like light duty vehicles are a great example. Building heat for new buildings in mild climates is really obvious. We should use heat pumps, this kind of thing. And those light duty vehicles and the heat pumps actually help fulfill that first goal of efficiency because the light duty electric vehicles and the heat pumps in mild climates are more efficient than your alternatives. Then the third priority is clean molecules for the parts of the economy that are hard to electrify. And I'm thinking industrial heat, maybe building heat in cold climates in old buildings, aviation, marine shipping, chemicals. And then the fourth one is carbon management, which is to remove the carbon that we couldn't avoid through clean molecules and electrification. So it's like the first few steps are kind of like do your best. And then the fourth step is clean up the rest. So that's kind of the saying, do your best, clean up the rest. So the 4 steps, efficiency, electrification, clean molecules, carbon management. Well, those last two, clean molecules and carbon management, are in the molecules business, probably going to be oil and gas companies or oil and gas adjacent companies. And those clean molecules could be biomolecules, biomethane. It could be fossil molecules of carbon capture. That looks pretty expensive to me. Could be hydrogen from a variety of sources, ammonia, methanol, formic acid, you name it. There's a variety of ways to get clean molecules. But in our analysis, if you want to get to zero carbon or net zero as quickly, affordably, reliably, and equitably as possible, it's cheaper, faster, more reliable, and equitable to keep molecules in the mix than to exclude them. If you have to go 100% electrons, it delays the path, makes it more expensive, and might make it more fragile or less robust because you have single point vulnerabilities and that kind of thing. So that's kind of my long speech. Like, I think molecules have a role, and I think it's in our interest to have molecules have a role. And I think it's certainly in our interest for the companies that know molecules to be on board with decarbonizing, and we can sort of map out a pathway. Here are all the ways an oil and gas company might make money in a decarbonized future, because I'd much rather have those companies on board with the future than against it.
Yeah. I think two things are true here. One, electrifying everything possible, everything that makes sense from an engineering and physics and financial perspective, that's good. There generally is energy efficiency, as you pointed out, right? The electric car is what, you're the engineer, what, 80-90% efficient versus an internal combustion engine car that wastes so much heat, right? And is only
Right.
30 or 40% efficient. So that's great. It's also, I think, important for people to understand that at this point, only 20% of all energy is electric. And even in International Energy Agency's net zero scenarios, at the very high end of the spectrum, you're talking 50 to 60% electrified energy. And so you still have a lot of molecules. So having those molecules be clean molecules, whether it's 40% or whether it's 70%, that's still a lot, and they need to be clean, right?
It's a lot that need to be clean, and even beyond that, we want those companies who know how to do it to be a partner for all the other things we need them to do, drilling and offshore and everything. Like, so it's the same companies often, and I see this role for molecules in the future. Now, another way I'd say it is, I think the total volume of molecules is going to be much lower in the future because we're going to replace a lot of molecules with electrons, but the uses of those molecules will be more valuable. And so when I talk to oil and gas companies, like, okay, would you rather sell more oil and gas or molecules, or would you rather sell fewer molecules but more profitably because you're selling them for very valuable procedures or processes, making cement or whatever it is, or doing backup power if you have no other options. So you're only using it for really critical times or valuable goods. I think like backup power is a great use of molecules, but when you need backup power, the prices tend to be very high. So it's a very profitable time to have natural gas for a natural gas power plant. But if you're using natural gas when it's really windy and sunny, well, that's a pretty dumb time to use natural gas because it doesn't really add value to society, and you're not making money off the gas itself either. So we burn a lot of natural gas that we don't really need to burn, but we could be using wind and solar. And so I'd rather save the gas for the high value critical times. And I think that's better for the gas sellers too. I think they'll make more money.
Yeah, I think it's really interesting on this question of oil and gas companies and what their role in the energy transition is. You know, I named my company Stoic Energy. I'm very into Stoic philosophy, and for instance, the books of Ryan Holiday, a fellow nearly Austinites and Bastrop. But he wrote a book where the title is "The Obstacle is the Way," and I think there's something really true there, that a lot of people view this as oil and gas companies are in the way, and sometimes that's quite true. But some of them are trying to figure out how to get through this transition. And I think the ones that just continue to be stubborn and intractable, you know, eventually there's going to be a decline there. This is like Clayton Christensen, innovator's dilemma stuff. Like, they have to like look around for the other things that are going to start to grow: clean molecules, hydrogen, carbon capture. Exxon bought a lithium mining operation, right, not long ago. I mean, it's
Right.
fascinating what is starting to happen, and it's slow, and it's too slow. There's probably a lot of people listening right now that are like, what are you talking about, and are frustrated by this. And I acknowledge it's too slow, but that's not the same as saying it's not happening at all.
We are actually, and the good news is we're making progress. The bad news is we need to pick up the pace a lot, right? It's just way too slow. On the oil and gas companies, there is a big distinction between the multinationals and then the independents, the smaller mid majors or domestic producers. And even among the multinationals, there's a distinction between the European multinationals and the American multinationals. Although the American multinationals are catching up to the European multinationals. European multinationals, Equinor, Total, others are fully on board. They're investing money. They have ambitious plans to ramp up their electrons business, to decarbonize their molecules business, that kind of thing. Equinor is really doing it. Ørsted, we think of as an offshore wind company. Ørsted used to be Danish oil and gas company, right? That's a European oil and gas company that is now fully on board with offshore wind and electrons. So I think we can look to the European multinationals for leadership on this. The American multinationals, you mentioned ExxonMobil, but there's others like Chevron and others who are also doing it. The smaller mid majors tend to be the laggards on this. They don't have the resources for it, but sometimes the leadership is just not on board philosophically with this. Or they're in a position where like, I'm going to retire in 20 years. That sounds tough. I'll just kind of ride the tail and make a lot of money the next 20 years and not worry about it. So the oil and gas industry is not quite monolithic on this. There's a lot of disagreement within it. And it's fascinating to me as a Texan. I think you see the same thing. The multinationals in Texas are not influential with Texas government, which is kind of a fascinating thing. That the local independents have much more say with the governor, lieutenant governor, other people than the ExxonMobils. And that's not true for ExxonMobil, I would say, in every other place where they're active. They're probably very influential. So we have some unique to Texas experience that might inform our opinion on this too.
It is a fascinating dynamic here, as so many things in Texas are. I want to back up and just kind of widen the aperture here. In your book, Power Trip, you talk about, and I'm a student of history. I love talking about history. I love taking sort of this broader view, and you do this so well, of sort of the evolution of energy sources and how we have seen better and sort of better, however you can define that different ways, more energy dense, I guess would be the best way to define that in this context, but cleaner as well, sort of one after another supplant energy sources before them. Can you just kind of run through that and bring us up to where we're at right now with the energy transition?
Yeah, and the history teaches us that transitions are common in energy, and there tend to be episodes where transitions happen faster. So I think we're 10 years into a 30-year transition right now. And we've had them before with the rural electrification from like 1930s and 1960s, with the second industrial revolution of the 1800s, the industrial revolution of the 1700s. So we have these episodes where innovation happens more quickly, innovation on the energy conversion devices, making new machines like a steam engine or a gasoline car or electric computers. We have new devices that convert or consume energy and new forms of energy available. And when you have rapid convergence of changing forms of energy and changing uses of energy, that's an energy transition. So we're in one. This is, to my eye, at least the fourth or more. Like, so they're more common than we think. And the prior ones instruct us on what to expect. If I take just one example in the United States, where we cut down most of the virgin forests in America, we deforested, we cut down these trees to get the wood as both a building stock, a material for fence posts on the prairie, but also to build our homes, but also for heat, for cooking, home heating, as well as industrial uses. We would like use the wood to make industrial heat, but also to do coking, to make different, charcoal or different things. So we use wood as a fuel and a feedstock for materials and energy. And we cut down so many trees, we did so much environmental damage that trees became very expensive. So if you go to Maine today, they're beautiful forests, by the way. Those are all second growth or regrowth forests. Those are not the original forests. We cut them down. And as we cut down the forests in New England, then the eastern seaboard, we moved further west through Pennsylvania. Eventually, we cut down most of the trees in the upper Midwest, like Wisconsin and Minnesota. Well, it's getting harder and harder to cut down the trees and move them to the markets being Philadelphia, New York, and Boston. The trees are farther and farther away, or you have to go longer and longer distances to get the trees. That wood became very expensive. Meanwhile, coal in Pennsylvania is closer to market. Coal is a higher performing fuel than wood. It gives you more energy density per pound, and it burns more cleanly than wood. It gives off less smoke and generates less ash and gives you less CO2, frankly, per unit of energy as well. So coal comes along and it's closer to market, it's higher performing, it's cleaner, and it's cheaper. So we start to use a lot of coal in the 1800s, and that leads us to stop cutting down the trees and the forests grow back. It's an incredible environmental solution at the time. Same kind of concept with whale oil as an illuminant, where we used whale oil. We kill these whales just to get the blubber, to get the whale oil as an illuminant, as a lighting fuel. And we killed so many whales, whale populations declined so rapidly, it became much more expensive to get the whales, and therefore the whale oil expeditions would take like 2 years instead of 2 months. And so whale oil became more expensive. Meanwhile, Pennsylvania comes to the rescue again, drill for oil in 1859 in Titusville, Pennsylvania, and you get the oil out of the ground. And if you refine or distill, think about it, that barrel of oil, the middle slice, the middle distillate is kerosene, which is a great illuminant, and it burns brighter and more cleanly and without the pungent smell of whale oil. And it's closer to market and it's cheaper. So with wood to coal and whale oil to kerosene, We went to these fossil fuels because they were cheaper, cleaner, better, higher performing, closer to market. And that let whale populations recover, let the trees grow back. And that was a great environmental solution. But now we're trying to clean up those messes. So one of the lessons here is there are solutions. We tend to move towards cleaner, cheaper, higher performing options. We tend to introduce new problems with those solutions. So coal and kerosene were solutions, but now are problems. And now we're trying to solve that with electricity or wind and solar, which is great. But if we do a lot of solar and a lot of wind at scale, they will introduce different problems, land impacts or mining or blight on the land or whatever your concerns might be. So you have to think about how to avoid those problems of doing them at scale and what we might do in the future to clean up whatever problems they introduce. And by the way, wind and solar are cheaper and cleaner, and I would say even higher performing in a variety of ways. They're not dispatchable the same way, but they're domestically located, and they have all these security benefits, which is China and Vladimir Putin can't turn off the wind or the sun, right? So they give us some other performance benefits. So that's where we're headed. But because they all have their limits, we'll do more than wind and solar. We'll do these clean molecules or geothermal, or we'll have other options because they all have their different upsides and downsides. So that's kind of the story of energy transitions. They happen quite often. It gives us some lessons. We typically move to a better place.
And there's a couple different places I want to go from there, but there's something you just said there that was really interesting at the end, and I do want to ask you about this. So, yes, China can't turn off the wind or the sun, but something like 90+% of solar panels are coming from China. There was a major change in U.S. policy in the Inflation Reduction Act, which I've heard described as not so much a climate bill as an industrial policy bill. Are you starting to see? I know you again, through not only being a professor but with Energy Impact Partners, you see things going on in the market. Are you seeing that have an impact on manufacturing here in America?
Absolutely. So first of all, the wind world is different because most of the wind turbines are made by Vestas or GE or Siemens. So these are Danish, German, or American companies. So the wind turbine manufacturing is not dominated by China the way solar panel manufacturing is. And one of the reasons why solar panel manufacturing is dominated by China is partly because of the mines for the silicon, the raw materials. The bigger concern I have is lithium or cobalt, or whatever, different, name your material. China probably dominates the market for the upgrading and refining of it, if not the original extraction. So China has a stranglehold on particular materials that are very important. And those materials might go in that wind turbine made in Germany, but they will go into things like batteries and solar panels as well. So there is a national security risk for these new options, but it's a capitalized risk. Like it's a risk in the manufacturing, not in the operation. So China might be able to turn off the flow of solar panels, but won't turn off the sunshine. And so they could disrupt our ability to build solar, but they don't disrupt our ability to operate solar. That's a pretty important security benefit. So there's still some security risk. It's just shifts in terms of scale of disruption and where in the supply chain or the life cycle of a facility it might be impacted. And because of that concern, and this is not a new concern, I was at a briefing in 2007 or 8 with Department of Energy where they were talking about this back then. They're like, we're really concerned about molybdenum and yttrium and erbium, like these different rare earth materials, as well as the silicon and lithium and cobalt and graphite and things like that. So they've been concerned for a while. They've been raising the flag of concern. So there's been a while to look at it in bipartisan interest in solving this. And the latest policy push with Inflation Reduction Act and others has these domestic sourcing requirements or supports for domestic manufacturing capacity. In effect, there's been tremendous uptick in domestic manufacturing capacity of electric vehicles and batteries and things like that. Probably won't go to solar panels that much, frankly. It'll be a little bit with for solar, but it's more like on the other materials. And where my venture capitalist hat, we're seeing some pretty interesting startups on domestic sourcing capabilities for new alternatives to graphite or new ways to manufacture anodes or cathodes for batteries, that kind of thing. We absolutely see startups that are ready to solve this problem. And not only is there like federal policy support potentially for the startups, but there are a lot of buyers who are willing to pay more for a shorter, more secure supply chain. But it's like they want to have a supply chain that works.
Michael, is that specifically about cobalt, or are there other issues when you talk about anodes, cathodes, and the different ways of
graphite? I think so there might be ways to do the lithium ion or the graphite's a pretty interesting one. Cobalt's fascinating. Cobalt, there it's less about China, more about the Congo, for example, where in there it's more of a labor justice issue than environmental justice. You have to worry about both. You have to worry about dirty mines, extracting materials that pollute the environment. You have to worry about labor justice issues, which might be 12-year-old boys in these mines in Africa getting cobalt out of the ground or prisoners or slave labor in China making solar panels. You also worry about the security risks of bad actors turning off the supply of the materials we want to make things. And China has already said they're going to do that. So these are all real risks. Cobalt's a little interesting, it's different to me in my perspective. When I was at ENGIE in Paris, we were very sensitive to labor issues. And for ENGIE, it was easier just to find an alternative to cobalt, like use a different material than it was to find an alternative cobalt source. So you could either find a different place to mine cobalt so you don't have the child labor issues, or you just find an alternative to cobalt. And companies are looking at, okay, how do we avoid that material? Or how do we avoid that country or that mine or that company, that kind of thing? So you can do a combination of the two, but there's some materials like graphite and lithium that it's going to be hard to avoid these materials. And frankly, of all the things I just said, the one I'm actually worried about the most in terms of total volume is copper. I don't know how you avoid copper in an electrified future. And I'm less worried about the environmental and labor risks there, but more just the volume. Like, is there enough? And can we get it at a price that's manageable without depending on countries who hate us?
I want to come back to something else you were talking about earlier. One of the things you thought that was wrong or commonly understood is the need for baseload power. That's interesting, because I do think there is a very, very common perception out there, like maybe 90%, even to people still in the industry, that you got to have baseload power. You got to have stuff that's always on. Why is that wrong?
I think it is hard for people to let go of that term because we've built up the concept of it over a century plus. The way we built our grid in the United States and elsewhere is to be load following. So you and I, we're turning on our lights or on and off, we're turning things on. So people like you and me, multiplied by hundreds of millions in America, we're turning on or off our loads. And then we ramp the power plants up and down to follow the load. So we set up the power sector to be load following. The loads change, however the loads change, based on the weather, temperature, time of day, whether we're at work or home, or how big our refrigerator is or whatever, and the power plants must follow. So it's load following. And then there's certain minimum load that happens throughout the year. We call that the base or the base load. And we have enough power plants that are on all the time to be base load to meet that minimum demand. And then we have peakers or mid-merit dispatch or other things we ramp up and down to meet the variability in the load above the base load. We built up that concept over 100 years and we have trouble letting go of it. Right? We need base load power plants. And we might need base load power plants, but we're moving into this new world where we don't just have variable load, you and I changing our habits and patterns during the day with light bulbs and things like that, but variable supply, because we have more supplies that depend on meteorological or astronomical conditions like the weather or position of the earth relative to the sun with wind and solar or hydro and that kind of thing. So add to the mix variable supply and variable load. I think load following doesn't make as much sense. In fact, I think we probably need supply following loads. Rather than turning power plants on and off to match when the load is, we should turn the loads on and off to match when the supply is. And those loads could be some non-critical data centers, water treatment, certain types of steel mills. There's a lot of things, pool pumps, water heaters, a lot of things we can turn on and off to match when the power is available, rather than turn the power on and off to match when the load is desired. So I think we need to switch our mindset from load following to supply following. And then if you do that, base load's a ridiculous concept. The way Brad Jones used to say it, and I miss Brad dearly, and I'm really sad that he died not too long ago. Brad was really just a great executive in the power sector. He was a public servant at ERCOT. He was a public servant at New York ISO, at New York Power Authority. Then he came back to ERCOT just as a gentleman to be an interim CEO after Winter Storm Uri, and recently died. And the way Brad would say it, and I really liked, he said, I need things I can turn on and off. He didn't use the word baseload. And it's like, it was almost like the way he was addressing this. Like, we need to change our thinking and our language even, because I need dispatchable things. And a thing that I can turn off is dispatchable, and a thing I can turn on is dispatchable. And Brad would say nuclear power plants are not dispatchable because I can't turn them down. Once they're on, they're on. At least that's true for American nuclear, by the way. French nuclear is very different. And so we would talk about nuclear as baseload because it's on all the time. It serves its need. But Brad would not call it dispatchable. And I agree, frankly. And so we need to get to this dispatchability, things we can turn on and off. And I think that's the future. And the dispatchability terminology should replace the baseload terminology. And by the way, designing nuclear power plants to turn on and off is entirely possible. We do it in other places around the world.
Yep. And I think it's dispatchability. I think it's also important to consider right there next to it, like a twin, flexibility, right? So it's like, yes, you want it
Absolutely.
always.
Yeah.
Yeah.
Agility.
Yeah.
Absolutely. Yeah, that's right.
Right. Right. So, and if you start to think about, I mean, you went through a list of the sort of demand that is flexible. I'll just add a few to it because we were talking earlier about carbon management. Big carbon dioxide capture machines, right, can be flexible. You don't need to run them 100% of the time. If you run them 90%, that's more carbon than we were capturing before, right?
Totally.
Flexible loads, green hydrogen you were talking about, or you just talked about hydrogen generally, but green hydrogen, desalination, there's all these different things. And actually, I think it's important for us to start thinking of storage itself, not only as supply, but as a flexible load, right? Because a lot of people
Totally.
say, well,
Yeah.
yeah, like data centers are this big growing demand, but they're not very flexible. That may be wrong because there's certain kind of data centers that will be flexible, but there's others that aren't. But if you put storage there, right now you do have a flexible load and a supply. So I really think that in many ways, battery storage is sort of the ideal dispatchable and flexible, um, demand and supply, right? It works both ways.
I agree. In fact, the way I think about it is electric vehicles will either save the grid or destroy the grid entirely dependent on what time of day you charge them, because they are this flexible load. And if we all charge at peak times, it can break the grid. But if we all charge at off peak times, it will save the grid because it will help us amortize our entire cost of the grid across more kilowatt hours and therefore lower the cost for all of us and give the money we need to do the investments to modernize, upgrade. So, and that's because the battery inside is very flexible. You can charge it easily. You can turn it on and off. You can do it at different times. Batteries have a response time of like 100 milliseconds, so they're really fast. So batteries are an important part of that flexibility, dispatchability, both on and off. That's really great. Some things we can only turn on, or other things we can only turn off, right? So it's nice to have the two-way capability with the battery.
Yeah, and in many ways, that then becomes the battery storage and its ability to be a flexible demand matched up with supply. It becomes another form of energy efficiency. And you talked about efficiency earlier when you said there's kind of these four steps: efficiency, electrification, clean molecules, and then carbon management. And efficiencies number one. I know you've done a lot of work on this. You've done a number of studies on energy efficiency. You've read a lot and talked about a lot about energy efficiency. Can you talk a little bit about its importance, specifically in a Texas context? Right, we've just come through another winter cold blast. Obviously, Uri is only 3 years in the rear view, and I don't think is getting much further from anybody's memory. Even the further we get, it's still sort of with us in all these conversations. But talk a little bit about energy efficiency and how it also plays into this flexibility discussion we were just having.
It's great. And from the United States perspective, the two biggest opportunities for efficiency are the building stock, our homes, especially, but homes and businesses. And then second is our vehicles, our cars. And those are the two biggest opportunities. There are many other things. Light bulb efficiency, for example, has been very dramatic in the United States. Our energy consumption has dropped as a nation, partly because of the switch to LED light bulbs, which are much more efficient. But the light bulbs are much smaller than gasoline combustion engines in cars or how much energy we consume in our homes. Light bulbs are part of the homes, but truly heating and cooling is a dominant part. And so efficiency there will do a variety of things. And efficiency at the home could be better insulation, better windows, better design, not having your windows face south in an unshaded manner if you're in Texas, but maybe face south unshaded if you're in a northern climate. So you can think about how you design your house, how you orient your house, the materials you use, the type of insulation, the type of windows, in a lot of passive things. And then you can think of the active devices, the heaters or coolers, and what kind of device and how efficient they are. Are they modern, vintage with high efficiency ratings? Are they pretty old and unreliable and more energy consumptive? There's a lot we can do there. And I mentioned earlier that I think that's a place for building codes. Our building codes are non-existent or weak in the United States compared to, say, France, where I was for a long time. France and Germany have much stricter building codes. They tend to have national building codes. In the United States, it tends to be either state by state or city by city. We don't have a national efficiency code, really, other than maybe for the devices like light bulbs. California has some strict building codes. They've avoided a lot of energy consumption over the last few decades. They call it the Rosenfeld effect because Art Rosenfeld really pushed for these efficiency rules. So the building stock in California is much more efficient. It's also a milder climate. And so they save energy, but their energy consumption wasn't as high to begin with. In Texas, our climate is less mild. We have drought and freeze and flood and heat wave. We tend to have it all. And we don't have strong building codes. Maybe City of Austin does, but it's not universal across the state. If you have a stricter building code around the devices and the passivity with which you design the home in a way that keeps it more efficient, you reduce how much energy you need dramatically. And therefore, you can have a smaller air conditioner, for example. And if it's a smaller air conditioner, it costs less. You can afford to pay more for a more efficient one. And then the safety benefits are remarkable. If the power goes out, your home will stay cool for longer. So you have this human health benefit and this quality of life benefit where you're less likely to die if you're a retiree and you're in a home that doesn't get as hot as quickly. And this happened in places like France in the 2003 heat wave. Tens of thousands of people died, especially the elderly, because their homes were designed to stay hot in the winter and they could not shed heat in the summer. So even there with their efficiency, their envelope was so tight, it actually kept the heat in. They didn't design around cooling. So elderly people can die if it gets too hot. That's a risk in Texas. Or if it gets too cold and the power goes out like Winter Storm Uri, your home will stay comfortably warm for longer. So efficiency has the benefits of saving the consumer money, making it easier to increase your efficiency again. They get these amplifying gains of a more efficient house needs a smaller air conditioner, which becomes more efficient, so it can be smaller again. And then you get better safety. That's a huge opportunity for us in the United States. We just aren't tackling it. And the analog is like lightweighting. You think of like major airplane manufacturers. If they go to a lighter design by removing redundant components, then they can have a smaller fuel tank. And if you have a smaller fuel tank, the plane is lighter again, which means you have smaller engines. Well, if you have smaller engines, you don't need as much fuel. And you get this like accelerating gains as you improve that way. Efficiency has the same kind of amplification or acceleration. The other one is gasoline cars. And going from gasoline cars to electric cars is a huge step in the right direction. And going even further, not just cars, but mass transit, walkable cities, bikeable cities, and the e-mobility or micro-mobility, e-scooters and e-bikes. That's really where you get efficiency gains. And that's, you might call that more conservation because it's more about the design of the system rather than just the individual device. But between conservation, how and where we lay out our transportation networks and homes with urban planning, and then the efficiency of the devices, the installation, the drivetrain or whatever, we can save a lot of energy that solves our problems, that avoids a lot of CO2 just in the reduced energy consumption. Then if you decarbonize the energy, you get additional gains. And then it saves money for consumers. So it's just like win-win-win and while improving resilience. So this is the obvious thing to do. But I will tell you, as a venture capitalist, it's hard to find investable startups in this space. It's a very awkward business case. And that doesn't mean it's impossible. There's certainly business cases for the industrial sector where they have really big energy bills and they have dedicated experts on staff just to look for cost savings in energy. It is already cost effective and market based for like school districts, but for an individual homeowner, efficiency can be hard to get to. And so I think that's where you have an opportunity for policy.
Yeah, there's so much there. It is difficult because it's such a diffuse market, right? By definition, you're talking about, what are we, 11 million residential units in Texas or something like that?
Yes.
It's just,
and the payoff is delayed. So the big mismatch right now is because we don't put a price on pollution, the cleaner things, which are often the more efficient things, cost more upfront. You pay more CapEx, more capital expenses, but they cost less to operate. So your OpEx or operational expenses go down. And so we're doing a more expensive thing up front to have something less expensive along the way. An EV today often is more expensive than a gasoline engine, but cheaper to operate. Triple pane windows are more expensive to install, but cheaper to operate. More efficient air conditioner is more expensive to install, but cheaper to operate. And if you are an individual, you're going to be pretty price sensitive to that upfront price. If you're the University of Texas, or if you're the federal government who owns a bunch of buildings, or if you're ExxonMobil with a refinery, you can do that trade-off of CapEx versus OpEx because you're pretty sure you're going to be at that site for decades. But if you're a homeowner, you might leave in 3 years and your payback might be in 4 years. And so it's harder for us at the individual level to make that trade-off. Also, we're pretty bad at math in general. But even if we can do the trade-off, that doesn't mean we can get the loan for the extra $10,000 on the house price or whatever. So there's some pretty fundamental.
And even if we could get the loan, it's like, do we really want a loan for that, or would we rather upgrade the kitchen or a bathroom? And everybody deals with this
exactly.
Sort of, so you are a mechanical engineer. I want to ask you about heat pumps and resistance heat. So You were just talking about efficiency, right? And I think a lot of times what people don't understand about efficiency, still a lot of people's perception of efficiency is you're asking me to suffer to, but it's actually the opposite, right? You're getting the same output or sometimes better output, but just using less units of energy. So LEDs are just a great example of this, right? You're using 1/10 or even 1/20th the amount of energy, but the light's actually better. It's dimmable. It's all of it's programmable. You could control it. It's all of these added features, and it's using less.
And it lasts longer. Now it lasts 20 years instead of 8 months too, right? So you design
There you
houses
go.
with light bulbs with the expectation you're never going to change the bulb. It changes the
Yep.
way you might design things.
So let's talk about that in a heating and cooling context. I mean, you were talking about how hard it is to invest in these companies, and you just have this mismatch in the economics here, right? So most homes are built with an air source heat pump that will heat it down, because we're 60% electric in Texas. So most homes are built with that heat pump that is only going to heat the home down to about 32 degrees and then have resistance heat as a backup. My understanding from talking to folks in the industry is that you can install resistance heat for a couple of $100. But on the power grid side, to build generation to serve that $200 resistance heat can be $10,000 or $20,000, right? But the homeowner, the builder, or whoever's paying the bill for that resistance heat isn't thinking about that, understandably so, right? But we're all going to pay for that power generation to serve that resistance heat. There are now resistance heaters that are cold weather rated that will go down to zero or even below that. And I think to a lot of people, it's like, well, how does that even work? How can it still be efficient? And of course, it gets less efficient the colder it gets. But can you give just a brief tutorial on, again, you're a mechanical engineer, so heat pumps and why they're so magical and how the sort of newer generation is changing things?
I think it's great. So the heat pump technology, and also will vary on where you are. So its value in Texas might be different than Vermont or France. And I'll kind of walk through all that. So the cold weather heat pumps get better and better every year. But if you're a homeowner, you're at some point confronted with a choice. Do I want to get the heat pump that can keep the house warm when it's 32 degrees outside, like you said, or the one that works even when it's 15 degrees outside? And the difference in price might be $1,000 or $2,000. Okay, do I pay $1,000 or $2,000 more for the cold weather heat pump, or do I just get the sort of cold weather heat pump and add a couple $100 of resistance heating? And for the homeowner, the resistance heating feels a lot cheaper, right? Looking at the math, that's saving me $800 or whatever it's saving. But then your electric bills will be more than $800 higher over the next 20 years. But that's really hard math to do. Like it's hard to imagine, you don't know how long you'll be in your house as well, but how much higher will the rates be for electricity? Because I and all my neighbors are adding resistance heaters. Therefore, we need to build more power plants. The cost of those power plants are spread across my bill and others, and I'm going to pay for it one way or another. And so that heat pump for the cold weather rating, even though it's more expensive, is probably cheaper across the system, though it might not be cheaper to you in a very direct, obvious way. So that's part of the challenge. And I would say, without a doubt, in mild climates, heat pumps for new construction are the way to go. They will save you energy. They're cleaner. They don't have the fumes, more reliable, all that kind of thing. If you're in a cold climate like Vermont, you can argue a little bit more about whether it makes sense. And if you are doing a cold weather heat pump, they exist now. You can install them. They work just fine. We know people who have them and they work fine. It costs more. And that heat pump is probably instead of fuel oil, which is particularly expensive and dirty. So you might not mind paying more for the heat pump because you're offsetting this expensive fuel. However, your other option might be natural gas furnace, and natural gas will be cheaper and cleaner than fuel oil as well, but not as expensive as a heat pump. So in many ways, like it gets more complicated in cold weather environments, especially if it's a retrofit. So if it's a new house you're building in Vermont or Maine, you can build the panel the right way and all that kind of stuff, do the heat pump. But if it's a retrofit where you don't have a big panel and you could just swap out gas or propane for fuel oil, and you're changing like the tank for $400 and you're getting cheaper fuel versus having to upgrade the panel for cold weather retrofits, going to a cleaner fuel will be cheaper and cleaner, but not as clean as a heat pump, but it'll be cheaper than heat pump. So you have to distinguish between, is it retrofit building stock or is it new building stock? And is it cold climate or mild climate? And certainly for new buildings in mild climates, it should always be heat pumps. Probably for new buildings in cold climates, it should be heat pumps. For retrofits in cold climates, it's kind of complicated. So we just got to talk. And the other thing is we start to moving a lot of power on those cold climates through the wires, and you can move more energy by pipe than by wire. So it might be cheaper just to decarbonize the fuels and use synthesized methane from hydrogen or something like that. And that's the case in France, by the way. So France is a cold climate situation. They have trouble upgrading their panels in those old buildings, but they already have the pipes for gas, so it'd probably be cheaper for them to do biomethane. However, in France, you get a different benefit. If you install a heat pump, you get air conditioning. And most of those homes don't have air conditioning. So in France, there's a movement for heat pumps, not so much because it improves the quality of the heating, but it's hot in the summer. They kind of want the air conditioning you get for free. You also get the benefits of avoiding Russian gas, that kind of thing. So the motivation between a Texas new building versus old building, Vermont new building, old building versus France will be kind of different based on what you already have or not.
So let's talk about Texas a little bit more, since we're focused on energy capital on Texas. If you, I think there's a lot of the heat, no pun intended, in these discussions is around electrifying everything and converting from gas to electric, and that's its own conversation. But let's set that aside for 1 second. We are more than 60% electric heat in Texas. So as somebody's HVAC is breaking and they're considering a replacement, a heat pump that has that cold weather rating, which like you said, will cost a little bit more. And you've said this before too, but I want to just drill into it a little bit more. This is the place where policy comes in, because it is a clear market failure in the sense that to the individual homeowner, if you just let the free market, and I'm generally a free market guy, I do believe in Texas competitive electric market. I believe markets are very powerful to drive change and to improve lives and all that stuff. But there are places where it just doesn't work because the incentives don't line up. Me as a homeowner, like you were just saying, it's just cheaper for me just to have that heat pump down to 32 and let resistance heat do the rest. Well, if I do that, I'm now using 4 times as much in my home as I am on a 100-degree day, and just leaving it to ERCOT and power generators to figure out how to supply that 15 kW. How did that turn out for us during Winter Storm Uri? And even if you do figure it out, it's expensive. And now I'm leaving it to everybody else to pay that. That doesn't mean I'm a bad person for making that decision. I'm making a logical financial decision. It's cheaper for me to pay the $200. So that's where government comes in, and the utility programs can come in. The Inflation Reduction Act can come in and close that gap down to zero to make that decision easy for people. Does that all make sense, or did I miss something in there?
No, I think you got exactly right, because there's this mismatch in economics speak, and I'm not an economist, so I might get this wrong. It's really called mixed agency, or you have an agency problem. The people who are making a decision about what to pay are not the only people who are affected by that decision. This happens a lot with landlords, where the landlord has to pay for the new water heater, but it's the tenant that has to pay the electric bill for the water heater or whatever. And so the landlord doesn't want to pay for a $3,000 water heater. That's better when they can pay for a $1,000 one. They don't care because someone else. So there's a mismatch. When you're doing your resistance heating tape, you're not really fully aware of all the costs you're imposing on the system, because it's not directly exposing you. It might show up to you indirectly later on, blended into your bill in a way that's hard to decipher. So maybe your bill is $10 more a month for many months in the future because of that. But that's hard to anticipate or know or even decipher once you get there. And so that's part of the system cost problem. The other thing I'll say is with the heat pump, if you get down to 32 degrees Fahrenheit, whatever, your electricity is 10 cents per kilowatt hour, say at home. That's not that big a deal. But if you're turning on that resistance heating tape below freezing, usually that's a time when it's really cold and electric prices are really high. So you're paying 10 cents a kilowatt hour at that time because you're on a residential rate. But the actual cost in the system is more like several dollars per kilowatt hour, which means someone's paying that, which might be you indirectly at some point, or industrial customers or someone. And so we're not exposed to how steeply the price is increasing. The more you're using resistance heating, the more likely the prices are to be higher than normal. So there's a great non-linearity that happens, or exponential rate increase. And you're not exposed to that. So that's a real problem. If you don't see any benefit for doing the better thing, other people are bearing the cost of you having made that choice. That's a great place for policy to rectify this market failure. Either putting the full price on the system onto you with that decision or whatever it is, or doing low cost loans or incentives to just install the better system because there's some system benefit to it. The market fails in many ways on this. Part of it is because we have mixed timelines. The power plant has a 50-year timeline or maybe a 25-year timeline if it's solar and wind. Your HVAC system has a 10 to 20-year timeline. You're making a decision in the next 10 minutes because it just broke and the technician's there and you got to decide. So there's operational decisions in a crisis in minutes, heating, cooling over days or seasons, asset lives mixed from one decade to five. Like it's hard to make that all bridge together with one market.
Yeah, I think that almost ironically, those that are just sort of like ultra fanatical and religious about markets end up doing damage to them, because if you just have that small help to the consumer to make that right choice, then the market has a better chance of actually functioning and working. It's just too much to put on the market to create that really expensive power in those times of scarcity for the 4 million homes that have resistance heat. It's just, it's too much to put on the market. It's like a release valve, right? It's like, just let some of that pressure out so the market can work.
It is so hard. And ERCOT doesn't know who's got what, right? So they can't see beyond our meter and know what we have. And they also don't know how we're going to behave. They can do some models, this kind of thing. And if you look in the past, they really underpredicted what the demand was going to be when it was cold, because partly they don't see how many of us have these resistance heaters. And so people yelled at ERCOT, hey, you need to improve your modeling to account for all the resistance heating that kicks in when it gets really cold. So then ERCOT did updated modeling that showed the demand was going to be much higher than it really was. And so it's easy to be wrong where you're too low, or easy to be wrong where you're too high. And I'm very sympathetic to ERCOT because I don't know how you model this thing where you don't have the data or can't see it. But that's part of the lack of transparency. They don't know what we have. But also there's human behaviors involved behind the meter. And it might be they were correct with the high estimate of 85 gigawatts of load. And we all saw that and thought, holy crap, I'll do my part. Who knows? Maybe we responded behaviorally. We don't know, right? So it might be everyone's bad at projections, or it might be we are responding to correct projections and therefore the projection gets adjusted. And we don't really know. But the resistance heaters just make it harder because it's such a big load that kicks in all of a sudden and it's invisible to ERCOT until it's already happened.
So there's two more things I want to talk about before we end, and one is, you talked earlier about one of the things that'll be different, a decade from now, is there'll be, you hope and predict there'll be more sort of retail competition. You talked about more distributed generation and solar. I think one way this could go is we could start to see sort of markets for dispatchability and flexibility. Flexibility markets would be one thing you could call them on the distribution side. And if you actually have markets for that, you can start to see, you just said ERCOT doesn't know what's going on beyond the meter. If there are markets where people could be paid to reduce, right, then you start to see how much are you using, how much are you reducing, and the retailers can start to see, they already have some awareness of this obviously already, but I don't think it's very granular. Who's got that really inefficient heat that maybe I can target some incentive to help. And by the way, that's going to make them more comfortable. It's going to lower their bill. And they can always say no. That's how markets work, right? It's voluntary. You want to pay a higher bill and be less comfortable? Have at it. Freedom, right? Great. But if you want to participate in this market, here's a potential to get paid for that flexibility, right? And you wrote a great op-ed in the New York Times about how Texas has these very advanced systems for paying large users, steel mills, Bitcoin miners, big box stores, but really hardly any on the residential side. How do you see that kind of playing out? Is it, or I mean, it's kind of opaque. It's hard to tell, but is it just retailers offering more products and services? Some of these upstarts in Texas, like Tesla and Octopus, and David Energy and Oak Connect, the list goes on. Or do we need some kind of more organized market where buyers and sellers can find each other on distribution side? Or is it something else entirely I haven't thought of yet?
I don't know, and I'm surprised it hasn't happened yet in many ways. We do have retail competition in many parts of Texas where you can choose who your retailer is. So we have that level of competition. And there was some market innovation within that where people for a while used to do free nights and weekends or lower rates or different things, or lower overall rate, but you're exposed to the market volatility. And that really caused some people to lose a lot of money and go bankrupt. So there was some market innovation. but not a lot. And it was mostly just competing by brand loyalty and fidelity. Like, do you like my company's logo or do you like me or not? So there's some competition, but not a lot of competition. And that competition is mostly on who is sending you the bill for the electrons you got. Maybe some differentiation on whether it's green choice or clean energy or that kind of thing. But I feel like there's more, and I just can't explain why there isn't more aggressive competition there. I think the next piece, and this makes a lot of people mad when I say that, especially distribution utilities, is to open up the distribution wires and poles the way we've opened up the transmission wires and poles. So when deregulation happened, before that, it was integrated. A power company would own the power plant, the transmission lines, the distribution lines, and then they would own sort of the retail customer. But they broke that up. So now there's competition at the front of the wire. It's regulated for the wire, moving it from the power plant to the customer. Then you could choose who your retailer is. But we haven't done that kind of opening up of the distribution service areas. Think of the different parts of Texas where there's owners of the wires where I could participate in over these wires. I could sell my electrons to my neighbor. I'm going to be out of town for a month. I got solar panels. Boy, I sure love to sell that power either to my neighbor or local utility or whatever it is. So those kind of peer-to-peer markets or those distribution level markets don't happen. And it might take regulation to do that where those wires become common carriers. Think of like what happened with AT&T, where AT&T had to open up its wires for telecom in the 80s. And all of a sudden you had Sprint and T-Mobile, a bunch of other companies popped up. So we had more choices and that drove down the cost of long distance. Same kind of thing happened. But I think there might have to be some opening up of who owns the distribution, not just the transmission. How do you make that accessible to everybody? And how do you let even individuals participate? Then you get some more innovations that will happen then. Because there are a lot of people like, well, yeah, I'll put a battery in my basin if I can sell it to my neighbor in the summers when I'm in Colorado or something like that. You might get more active participation that way.
Yeah, there's obviously more resistance than openness to that in from what I've heard in the transmission distribution utility world. But I think there's starting to be a little opening there, partially because the utilities are understanding how big this challenge is.
Yes.
And they also live in these communities and see the reliability problems and see the costs going up. And I think there's becoming more of an openness. I think the other thing, Michael, the reason why there might be some openness to that is because there is such demand growth happening from electrification of transportation, new things like hydrogen or industrial heat being electrified. Their growth opportunities are so much that I think some of that, maybe somebody else is doing some of the smaller stuff, doesn't scare them as much as it once did. That's my hope anyway.
Right.
I don't know.
Me too. So yeah. We'll see. Yeah, we'll see how it goes. But I think there'll be some changes there. And we talked about distributed generation. If you have distribution level markets, it'll be easier for people to invest in distributed generation at their home. And you can kind of get to there with net metering, but net metering is a partial solution, but that's not quite a competitive market on the distribution level.
I got to ask you just one more thing, and this is kind of just a 90-degree turn, but I tried to loop it together there with the electrification piece. I don't know. It wasn't very elegant, but maybe I connected it as hydrogen. You said earlier that one thing you think is wrong is that hydrogen will forever require subsidies. So you think hydrogen's coming down the cost curve pretty fast. I know you've done a lot of work on hydrogen, and you're doing some work now, right, on some of these natural seams that exist for hydrogen, and you think this kind of big thing. Talk a little bit about where you think hydrogen's going. Maybe just talk a little bit about the difference between what is commonly called green and blue hydrogen, and there's other kinds too. But what do you think is most promising? Why do you think it's not going to need the subsidy? And how much are these natural seams going to play a part? And then we'll end there.
If you talk to the companies that make hydrogen, they're happy to have the subsidies, frankly, right? Who doesn't like to be paid extra for the thing they're already going to do? And the reason why I think hydrogen will eventually not need subsidies is just like all the other industries that might have received subsidies for a while. Once they develop maturity and a more robust supply chain, costs come down with learning. And hydrogen can be done at a variety of scales, small scale or large scale. We'll just do a lot of it. And as you do more, costs will come down. The ways you can make it include electrolysis, using electricity to split water to get the hydrogen out. Some people call that green hydrogen, especially if it uses like wind or solar. You can use nuclear electricity or geothermal, whatever clean electron you want to split the water. You can use steam methane reforming with carbon capture, where you start with methane, convert it into hydrogen, and it's done in a low carbon way if you have carbon capture and if your methane system is not leaky. You can also do pyrolysis, where you start with methane, and then you use a plasma or a catalyst or some sort to strip out the carbon. You get the hydrogen, but there's no CO2. You just get carbon black. And that carbon black can be used for graphite or solar amendments, that kind of thing. And pyrolysis looks really efficient and clean and lets you leverage existing infrastructure like natural gas pipelines, that kind of thing. So that's really interesting. There's photolysis and photobiological techniques and photoelectric techniques. My father looked at photodiodes to get hydrogen with xenon lamps out of water in the 1980s. So as a chemistry professor, so there's just a lot of pathways. And the one you mentioned is natural hydrogen or geological hydrogen. There are places where the earth makes it. You can make hydrogen by reacting water with iron-rich or magnesium-rich rocks under the right conditions. And we have those kinds of conditions many places around the world. And then you just have to extract the hydrogen from the earth or capture it from these seams. And then it doesn't take all this natural gas or electricity to get it. And so it ends up being cleaner and cheaper and less water intensive and doesn't impact the land. And there's just looks like there's a lot of it, and that's going to drive down the cost a lot. So there's some surprises on the horizons, and the headlines are really focused on electrolysis. But we just want to remind people there's a lot of ways to make hydrogen. The markets haven't chosen the winner, and the winner might look a whole lot better in the future than it does today. And it reminds me a little bit of where we were with computers in the 1990s, where every year computers got cheaper and better. So it actually became a problem. Like I used to buy computers for my research at grad school. I could buy a $1,500 computer, or if I waited 6 months, I could get a $1,500 computer that was like 50% faster. And this happened like every 6 months. I feel like we're entering one of those curves for batteries. We've been on that curve for batteries maybe for a few years, but we're about to enter that curve for hydrogen, where every 6 months or a year, it'll be a little bit better and prices might come down. And eventually that means the subsidies really aren't necessary. Maybe they're good to get the industry started. And I would say as long as you let other people pollute for free, you got to do the subsidy to bring it into balance. But I think that won't be necessary at some point.
What do you think hydrogen is mostly going to be used for, and what do you think it's not going to be used for?
I think hydrogen will be used primarily as a building block for high-value chemicals like fertilizer. And I think we might want more fertilizer. And if we use more fertilizer, we might need less other forms of energy to reap our crops and protect our foods and refrigerate and that kind of thing. So I think we'll have more agrochemicals, and hopefully not the kind that are cancer causing and that kind of thing, but the kind that help us lead to food abundance. I think we'll use hydrogen as a building block for things that are hard to electrify, like aviation fuels, for like long haul aviation. Short haul aviation, maybe we can electrify, probably for marine fuels. And that might be ammonia or methanol or something like that. We might build from hydrogen. You can also get there from alcohols, by the way. If you ferment biomatter, you might be able to get to the jet fuels or marine fuels. And then industrial heat. There's certain applications where you need high temperature heat, where we burn gas today. Burning hydrogen instead would be better. Some of the industrial processes can be electrified, but a lot of them just won't. So that might be hard to get there with like a heat pump, for example. And then maybe for long haul heavy duty trucking. I mean, there's a battle right now between electricity and hydrogen, or not necessarily hydrogen, but hydrogen as a building block for diesel. Long haul trucking might be another place where hydrogen is valuable. So there are the few places outside of the power sector, but then the power sector, hydrogen itself might be a good backup fuel because you can store it more easily than a battery for long duration. And I think that's a pretty good use of hydrogen. I wouldn't want to use hydrogen for round the clock operation of the power sector, but there are episodes where it's neither windy nor sunny, where it'd be nice to have a power plant that you could turn on still. So I think that will be either backup or peaking times for reliability purposes in the grid. So that's it. I mean, I don't think it'll be light duty vehicles, and I don't think it'll be home heating. I think a lot of things hydrogen won't do.
Yeah, and with that backup piece, you can actually make the hydrogen with the wind and solar when it's abundant, and then use it when the wind and solar is not. Yeah,
especially for like island communities where it's so expensive to bring in diesel, but they have abundant sunshine or wind. They would use electricity to make a storable form of electricity, say with hydrogen, that they can then use to make power later on.
I know I said that was going to be the last thing, but when you said island communities, I have to ask you about interconnecting ERCOT. You've talked about this a lot. We need to interconnect. Just this will be the last question. I promise. I need to let you go, but yeah, we got to talk about that. Do we need to interconnect, Michael?
Yes, and if we interconnect, it will make us money. It will save us money. It will reduce pollution, and it will improve reliability. Like, it's the most obvious kind of thing we need to do. And this is where Texas jingoism and nativism and patriotism gets in our way, where we don't want to do it because we don't want to deal with the feds or something like that. But we deal with the feds for natural gas exports, liquefied natural gas exports, crude oil exports, refined oil exports, wood pellet exports, you name it. We deal with the feds for a lot of exports of energy because it makes us so much money. So we're willing to deal with the TDM of federal regulators if it makes us money. But for some reason, we decided, well, we're not going to do it for electrons. We don't want to make billions of dollars a year. We don't want to save billions of dollars a year for consumers. We don't want to make landowners royalties, and we don't want to improve the reliability of the grid because we'd rather just build gas plants here. But if all we did was build gas plants here, which is the preferred policy solution in Texas, that will be much more expensive and dirtier. And we sort of cut off our ability to export a lot of clean wind and solar to other states who would like it but can't build it. Like California's running out of room to build stuff. They would love to import solar and wind from Texas. So I just think it's silly that we haven't done it. I know there are groups trying to do it with DC ties, different like Grid United and other people are trying to do projects to do these interconnections. It's a great idea. I'm really amazed we're taking this long to make this much money.
Michael, thank you so much for doing this. Anything you wanted to say that you didn't get a chance to, and also where can people find you on, social media or the web, your books?
Yeah, regrettably, I'm very active on Twitter and LinkedIn, and just my research group at UT is WeberEnergyGroup.com, and I'm also at Energy Impact Partners, and just there are a lot of ways to find me. My email is pretty easy to find, so send me a note. Really appreciate the conversation with you. You've become really one of the important thought leaders in this space. And despite it all, we end up often at the right answers in Texas, even if it doesn't look like we're going to get there. But we're kind of making our way towards the right answer, which is good news.
We take strange paths, but we sometimes end up in the right place. Michael, thank you so much. Appreciate it.
Thank you.
Thank you for listening to the Energy Capital Podcast. I hope you enjoyed the episode. If you did, please like, rate, and review wherever you listen to your podcasts. Until next time, have a great day.